Recording. Hi, so I'm going to be talking about continuous state branching processes and the connection these processes have with lambda coalescence. This is joint work with Amaury Lambert. So a continuous state branching process is a non-negative Markov process satisfying the branching property. The branching property states that if we have several independent copies of the process, starting from x1 up to xm, and we add together these independent copies, we get another copy of the process starting from x, where x is the sum of x1 through xm. This is best seen through a picture. Flipping our perspective slightly, if we have some number x, and we can write it as a sum of x1 plus x2 plus x3, then a copy of the CSBP starting from x can be represented as a sum of these smaller independent copies, zx1, zx2, and zx3. So the simplest example of a non-negative Markov process satisfying the branching property, i.e. a continuous state branching process, is given by solutions to this stochastic differential equation. So if you take several independent solutions of this stochastic differential equation and you add them together, then the sum satisfies the exact same equation. More generally, the only stochastic differential equations satisfying the branching property, or whose solutions satisfy the branching property, take this form, for some constants alpha and beta. So here alpha controls the sort of deterministic growing of the size of the process, and beta controls the Brownian component. So these alpha and beta will feature on the next slide. It turns out more generally that we can use the machinery of Levy processes to characterize all CSBPs. So it turns out that every CSBP is characterized by a Levy-Chinchin representation. So here we have alpha and beta as they were on the previous slide. So alpha's deterministically creates growth in the process, and beta controls the Brownian component. And here we have a more complex part, m. M is a measure which actually controls the rate of random jumps of the process. So CSBP can be understood as a sort of fuzzing solution to the SDE we had on the previous slide, plus random jumps. Now, this measure m has to satisfy some integrability conditions, which I won't discuss here, and you can have quite exotic choices of m that are infinite near zero, so you can have tons of tiny jumps contributing to the process. Now, thanks to work in the 90s, it's actually possible to endow a CSBP with a rigorous notion of genealogy. Namely, if we take any time little t, we can use the branching property and the Markov property at the same time to chop the process into tons of pieces and represent the future growth of the process, the future size of the process, as an independent sum of smaller processes. There's a beautiful construction which allows us to do this procedure sort of simultaneously at all times, little t, and chop it into as many pieces as we like. And this sort of procedure enriches the filtration of the process. And in this enriched filtration, we can discuss genealogy. Namely, we can create a rigorous notion of saying each particle B living at some time had a unique ancestor A living at an earlier time. This creates a blue sort of ancestral line going back, starting from every particle B going backwards in time. We'll be interested in picking several particles B1 up to Bn uniformly and independently from the time T population, and tracing these ancestral lines back in time and looking at how they merge as time passes. In order to do this, we need to introduce coalescent processes. So a coalescent process is simply a stochastic process taking values in a set of partitions of a finite set with the property that blocks merge as time passes. So here is a simulation of a coalescent process when n is equal to 5. And you'll see each block is represented by a line, and as time passes, these lines merge. So a lambda coalescent is a special type of coalescent process. So let lambda be a finite measure on 0, 1. Then the lambda coalescent is a special Markovian coalescent process whose merger rates can be described in terms of this measure lambda. Namely, if at some moment the process has k different blocks, and it doesn't matter how many elements are contained in each block, then for every j of these, for every subset of j of these blocks, and again it doesn't matter which j we choose, these blocks are instantaneously collapsing to form a single new block at rates prescribed by this integral equation. which has an interpretation in terms of a sort of Kingman paint box construction, which I won't go into here. So we'll be interested in connecting CSBPs with lambda coalescence. So as we saw before, a CSBP is characterized by an alpha, a beta, and a measure m on the positive real line. And a lambda coalescent is characterized by a measure lambda on the unit interval. We'll want a way of relating measures on the positive real line to measures on the unit interval. So it turns out in our main result we'll need the following construction. So you have the following map here, sending elements of the positive real line to the unit interval. And this map can be used to push forward mass from the measure m onto the unit interval 0, 1. So our main result states that, if you choose ancestral lines uniformly from a continuous state branching process with parameters alpha, beta, and m, and you trace these ancestral lines backwards in time, then the mergers of these ancestral lines can be characterized in terms of a sort of lambda coalescent equation. But here the lambda measure depends on the population size x. So this lambda measure is sort of changing dynamically in time. So if the process, this continuous state branching process, has parameters alpha, beta, and m, then the lambda measure depends on beta through this bit, and the measure m through this push forward. But actually it doesn't end up depending on alpha. Let's see some examples of this. So the simplest example of a lambda coalescent is Kingman's coalescent. This corresponds to the special case where lambda is the Dirac mass at 0. And it turns out when you calculate the rates of this process, you'll see that the integral equation tells us that we only ever get 2 blocks merging at once. Now, if we plug in alpha, beta, and m of Feller's diffusion, or Feller's continuous state branching process, so these are the special class of continuous state branching processes with no jumps, i.e. the measure m is equal to 0, then our formula tells us that the associated lambda measure is this multiple of the Dirac mass here, where we have the multiple is inversely proportional to x, the population size. So here we recover a result by Donnelly and Kurtz, which tells us that if we pick several particles uniformly and independently from the population of a Feller diffusion and trace their ancestral paths going backwards in time, these ancestral paths sort of merge like a Kingman coalescent. However, the rate of mergers is inversely proportional to the population size. So you'll see in this simulation here, there was a bottleneck in the population size where it was relatively small. People tended to be closely related during this period where the population size was small, and the coalescent events happened quite quickly as we approached this bottleneck. So a completely different example qualitatively is given by the connection between Neveu's CSBP and the Bolthausen-Schnittmann coalescent. So the Bolthausen-Schnittmann coalescent is the special lambda coalescent where lambda is the Lebesgue measure. And this coalescent process is characterized by having huge mergers. So for instance, if the process has, say, 100 blocks at some moment, you could instantaneously have 70 of these blocks collapsing to form a single block. So it turns out that there is a special continuous state branching process known as Neveu's CSBP. So this is the continuous state branching process with no Brownian component and whose jump measure m is has a density proportional to 1 over r squared. It turns out that this CSBP has its coalescent structure described in terms of the Bolthausen-Schnittmann coalescent. When you plug these alpha, beta, and m into our formula for lambda. Moreover, it's really worth emphasizing here that surprisingly this measure for lambda doesn't depend on x, the population size. In fact, this is the only continuous state branching process where the measure doesn't depend on the population size. This has the strange consequence that when we trace this ancestral path backwards in time, the mergers don't care at all about the size of the population process. And in fact, resultantly, they turn out to be a Markov process in their own filtration. So with no rescaling of time or time change, the ancestral process of a Neveu CSBP is Bolthausen-Schnittmann. So actually, we prove our result linking CSBPs and lambda coalescents in the more general multi-type setting. So a multi-type CSBP is simply d-dimensional Markov process satisfying a branching property in d dimensions. So here's a simulation of a 2-type CSBP with blue and red types. And this CSBP might work where each one behaves individually like a CSBP, but you could have red particles deterministically creating blue particles, or blue particles having a sudden explosion of red particles that they create. So you can have quite complex interplay between the different types. If you pick several particles uniformly from the blue population and several uniformly from the red population, and you trace their ancestral lines back in time, then we have a sort of multicolor coalescent process where you can have several blocks of various different colors instantaneously merging to form a single block of a different color, or a single block changing color, etc. And it turns out this coalescent process can be described in terms of a multi-type version of the lambda coalescent, where this multi-type lambda coalescent has d measures, where d is the number of types, and each one of these measures is a measure on the unit cube in d dimensions. So I won't give a full statement of our multi-type theorem, but I'll just talk about the simplest example. So the simplest example of a multi-type continuous state branching process is the multi-type Feller diffusion, the solution to this d-dimensional stochastic differential equation. So here the parameter beta I controls the Brownian component of the type I population, and the parameter kappa ji controls the rate at which type J particles create type I particles. So it turns out that the coalescent process of the multi-type Feller diffusion can be described in terms of a multi-type, sort of multi-color version of Kingman's coalescent, where again you can have two blue blocks instantaneously merging to form a single blue block at a rate inversely proportional to the size of the blue population, as in the single type case. But we also have the additional dynamics that you can have a blue block changing color to a red block at a rate proportional to the size at which red particles create blue particles, so kappa ji, and multiplied by the ratio of the red particles, number of red particles divided by the number of blue particles. And this makes sense if at some moment the red population is very large compared to the blue population, then it's likely that lots of blue particles are recent descendants from red particles. So going backwards in time, these blue to red changes of color in the coalescent process happen at a faster rate. You'll see in this particular simulation, there was actually a moment where the red population disappeared entirely and then was brought back to life from sort of immigration or mass creation of green and blue particles. Of course, going backwards in time, this means that if we trace the ancestral lines of the red population, they sort of have to evacuate before this bottleneck in the population size. So that concludes the talk. Thanks for listening. And the talk's based on this paper.